Hello, everyone, and welcome to today's live stream. Let me check my audio levels. Okay, looks good. Let me see how many people are in the chat. 0 people. That's okay. Uh, it was a last minute thing, and here it is. So what I'm going to do today is to not have too much repetition with the stuff that I did in the other 2 videos. I'm going to just do a 1D problem. I'm going to do 3 questions with a 1D problem, and I'm going to try to make it the last of the 3 is going to be fairly sophisticated, so it's going to be increasing in difficulties. Okay, a few people asked me about the 1D problem on the assignment, and I didn't do any 1D problems in the class for Physics 111, nor did I do a 1D problem in the tutorial video. So I thought I'd do one today. Okay, so let's just start. Okay, so we have a 3 kilogram mass, which is moving to the right at 3 meters per second, and it's going to collide with a 7 kilogram mass moving to the left at 2 meters per second. Okay, and the 2 masses are going to stick. And I asked the question, how fast and in what direction is the resulting mass traveling? And what is the energy before and after the collision? Okay, because whenever 2 masses stick together, 1D or 2D doesn't matter, but whenever 2 masses stick together in a collision, it's always going to be inelastic. In other words, energy is going to be lost. So the energy after is going to be less than the energy before. Okay, so a quick picture to what's happening here is this is our before picture. I'll draw the after picture in a minute. And you could think of like a linear track here, and you have a M1 is going to be like our 3 kilogram mass, and it's moving to the right at 3 meters per second. And I put that plus there to really emphasize that it's moving to the right here like this. Okay, so that's the positive direction. And we have the 7 kilogram mass, and it's moving to the left, negative right there at 2 meters per second, and they're going to collide and stick. So the after picture, what it's going to look like is we're going to have the 3 and the 7 kilogram mass stuck together like this. Okay, and so the total mass here, we can call it M primed. We don't have to say 1 or 2 because there's only 1. It's going to be 3 plus 7, right? Because mass is conserved as well as momentum, and so mass doesn't just disappear or appear from nowhere. So there we go. We have 10 kilograms there like that. Okay, and I don't know whether it's going to be going to the right or the left. Okay, so well, I do know because I solved the problem, but you don't know beforehand. So we'll just say V primed here, and we'll see what sign comes out of that. Okay, but basically that's what the after picture looks like, and it's either going to be going to the right here, or it might be going to the left like that. We don't know which way. Okay, so we don't know which direction, but that'll come out with the sign. All right, so how do you do that? Well, first you calculate the momentum before. Okay, and so to do that, you start off by you have to construct an expression for the total momentum. Every single mass in the problem contributes to the total momentum, the value mv. Okay, so basically m1 has a mass m1, and it's got a velocity v1, and so the momentum due to the first mass is m1 v1, and the momentum due to the second mass is m2 v2, and the total momentum is the sum of the two. That total momentum is what's conserved. Okay, and I call that p before the collision because it's before the collision. Okay. All right. So what do? Well, here you just substitute in the values. Okay. So you have 3 kilograms and it's moving to the right. We can even put a little plus sign there. Okay. So 3 kilograms moving to the right at 3 meters per second. All right. And you have a 7 kilogram moving to the left at 2 meters per second, and so that gives you a total momentum of -5 kilogram meters per second. Okay, now that's the total momentum before, but that's also the total momentum after. Okay, now for the next step, you're going to write down the total momentum after the collision, and again you have to construct that what that looks like. Okay, and after the collision, you take a look here, there's just one mass, okay, because the two masses have stuck together, and I called it m prime, and so there's only one mass and it's got one velocity v primed, and so the expression after the collision for the total momentum is just m prime p prime, m primed v primed. Okay, and if we substitute in our values here, we can actually substitute in a value for, here, let me put this on the next line below it like this. And let me put that on the line below it like that. Okay, so you can see the progression of the logic. So there's the expression there. Okay, get rid of that. Okay, and now we can substitute in. You say, well, do we know P after the collision? Yeah, it's got to be the same as P before, because that's the whole point of conservation of momentum. Okay, so that P after is equal to -5. The mass after is 3 plus 7, because the two masses have combined into one. Okay, and V primed is unknown. And then just solving, it's quite simple. You just get that V primed is -0.5 meters per second. Okay, and so if we go back to the diagram here, now we know that it's actually going to be traveling. I don't think I have my eraser here. Whoops, there we go. It's not working that well. Okay, well, good enough. So it's actually going this way like that. Okay. Sorry, that's not working out well at all. Let me see that. There, that's maybe a little better. Okay, so that's the direction. All right, so it's negative, that is to the left, 0.5 meters per second. Okay, and this is about as simple as they can get. Okay, for 1D problems. All right, but that's all right. All right, let's go to the next part of this problem. Let's answer the next part of this problem. What is the energy before and after the collision? Okay. Now, in these problems, we don't have any like springs. We don't have any like going uphill or downhill or anything like that. So the energy is purely kinetic. All right. But unlike when we did energy, I concentrated on just one object. Every object in the problem has its own energy associated with it. And so you want to calculate the total energy of the system. So you're going to have to add up the kinetic energies for each of the objects. All right. So the total kinetic energy before is going to be 1/2 mv squared for object number 1, mass number 1. Okay. So there's the 1/2 m1 v1 squared. Okay, and then plus the same thing for mass 2, 1/2 m2 v2 squared. Okay, now substituting in, we're going to get for the half here, that's 0.5, m1 is 3, v1 is 3 squared. Okay, and then for m2 we have a half right there, and then for m2 we have 7. Okay, so m2 is 7 kilograms, and v2 was -2 meters per second, but when you square a negative number, it becomes positive. And that's sort of the point of energy. Direction doesn't matter, and the sign is just whether it's traveling to the left or the right. But whether it's traveling to the left or the right, it's the same for the energy. The momentum is different because the momentum is a vector, so you have to have the sign for the momentum, but you do not need the negative or positive sign for the velocity when you go to calculate the energy. Okay. And so 1/2 mv squared there, and this turns out to be a total of 27.5 joules. Okay, 27.5 joules. All right, so that's the energy before, and the energy after. Okay, is just 1/2 m primed v primed squared. Okay, because there's only one mass. All right, and so substituting in, m primed is 10. There it is, 3 plus 7. And v primed, we just calculated that. It's this half, okay? And once again, I just dropped the sign, okay, because if you square negative a half or you square positive a half, it doesn't matter. It's the same number, okay? So the sign drops out, and that gives us 12.5 joules, okay? So this thing started with 27.5 joules. This system, the two masses coming together, started with 27.5 joules. They collided and they stuck, okay? And then the combined mass is moving off with only 12.5 joules. And you wonder, well, where's the difference, okay? And the difference, if you subtract 12.5 minus 27.5, you get negative 15 joules. Negative because that's energy which is lost to heat. It's converted into heat, okay? This energy is actually internally inside of the mass itself. So if you take a look inside the combined mass here, there's like when these things collide, it actually generates a little bit of heat there, and we'll see next semester that that heat is actually energy. Okay, it's measurable in energy units, and that's where the 15 joules went. Okay, so when things collide, there, especially when they stick, there can be a loss of energy. Okay, and this is what is known as an inelastic collision. Inelastic, because the energy after is less than the energy before. Okay, if you have a ball like a rubber ball and you bounce it, you notice that the rubber ball doesn't quite bounce to the same height as it did before. It bounces a little less, a little less, a little less. If you take the maximum height that the ball gets to, at the maximum height, the energy is all mgh, right? And so as the height decreases, that means on each subsequent bounce there's less and less energy in the ball. Well, less and less mechanical energy, or energy like potential energy that raises it up, but there's more and more energy in the heat inside the ball itself, internally in the ball, and that's where that energy is going. When these balls bounce, they'll actually go to heating up the ball internally, and so there's less energy available to raise it up to the same level that it was before. Okay, so there's our first problem, and about as simple as they get. Let me see if there's anyone in the chat right now. Nope. Okay, let me continue then, because there's no one in the chat. There's no questions. Okay, so same before, but now a different after. Okay, a 3 kilogram mass is traveling to the right at 3 meters per second and collides with a 7 kilogram mass traveling to the left at 2 meters per second. Okay, exactly the same situation as before. Okay, after the collision, the 7 kilogram mass is found to recoil with a speed of 10 meters per second to the right. Okay, so initially the 7 kilogram was traveling to the left at 2 meters per second, and it recoils after the collision to the right at 10 meters per second. Okay, how fast is the 3 kilogram mass moving after the collision? All right, so the picture there is going to be a different after picture. Okay, so let me draw that. So this is like after for question number, this is after for question number 1. Okay, here's our after for question number 2. All right. The 7 kilogram was coming in, it was coming to the left. It collides and it bounces this way. Okay, so this was M2, that's our 7 kilogram mass there, like that. Okay, and so this we'll call V2, and the little prime there just means after the collision. And then over here, the 3 kilogram mass, which I called M1, okay, that is traveling to the left at a velocity of v1 prime, like that. Okay, and let me see, what did I tell you here? The 10 kilogram is 10 meters per second, so we know that this one is traveling to the right, which is positive, at 10 meters per second. Okay, like that. And I wonder, I'm asking, how big is v1? Like that. Okay, so how do you do that? And also I ask, that's the first part, and then the second part I ask is the collision inelastic, elastic, or superelastic? Okay, so the total momentum before, I didn't even bother to show you how I calculated that, because the before picture is identical to above. So if you were to repeat everything you did here, all right, you would still get negative 5 kilogram meters per second. So even in question number 2, the before is a negative 5 kilogram meters per second. All right. The momentum after is, you can't calculate it this way. All right. You can't use that, because that worked when the two stuck together, but the two are not sticking together. They've just collided and bounced apart. Okay. And so over here, and let me put this on another line. It's a little bit too noisy. put these like that. Okay, so over here for the momentum after, you have to do m1 v1 primed and m2 v2 primed. Okay, again, the primed are the velocities after the collision. Okay, so in this particular one, I didn't have any masses like breaking off or recombining or anything like that. So there's just these the same two masses, the 3 kilogram here and the 7 kilogram here, but their velocities are different because after the collision, you know, they recoil. Okay, and so now you say, well, what do I do next? All right, so if you take if you say what's the value of P after, well, it's got to be the same as the value of P before, because that's the whole point of conservation of momentum. So for P after, we can put in -5 like that. Okay. For M1 here, we can put in 3 kilograms. Okay. And V1 prime, we don't know. Okay. For M2, that's 7 kilograms. And I tell you that it recoils with a velocity of 10. It's actually positive 10, just putting the plus there for emphasis, positive 10 meters per second. Okay, and you know, we can now solve for v1 primed. Okay, so I don't know, cleaned it up a little bit there, and now if I simply subtract 70 from both sides and divide by 3, I will get that v1 primed is -25 meters per second. Okay, now let's see if that makes sense. -25 meters per second. I already drew in the diagram that this was going to be recoiling to the left, and we now know that it's going to be recoiling to the left with a velocity of -25 meters per second, like that. Okay, so yeah, it kind of makes sense, you know, like the 7 kilogram goes off to the right at 10 meters per second. The smaller one recoils, but it recoils with a bigger velocity, 25 meters per second, but in the opposite direction, in the negative direction. Okay, so yeah, this kind of makes sense, you know, this diagram here. Let's see what happened to the energy. Okay, so this tells you what happens because of the conservation of momentum. What about the energy? Well, once again, the energy before is the same as in question 1, because the before picture didn't change. Okay, and that means if the before picture didn't change, it's the same initial momentum and it's the same initial velocity. Okay, it's the same, initial energy. Okay, the same energy before the collision. Okay, so that's still 27.5 joules. All right, now what about after? Well, after, let me put this on a different line so that it's easier to see. Okay, after, we got to use this to calculate the energy, because you have two objects. Okay, you have M1 moving with velocity V1 primed. Okay, and so the kinetic energy to that one is 1/2 M1 V1 primed squared. And the same thing for M2. Okay, now we know all these numbers because once I solve the part A of the problem, the first part of the problem, I know V1 primed, I told you V2 primed, you know M1 and M2. So you can substitute in all those numbers here like that, and you find that the energy afterwards is much, much larger than it was before. Okay, so before the collision, it was only 27.5 joules. After the collision, it's like 1,287.5 joules. And you say, geez, what just happened there? Okay, well, the energy after is bigger, and this can happen because of an explosion. So what you might imagine is that these two masses came together slowly, but maybe there was a little bit of like TNT between the two, and when the two touch, they go boom and they fly apart. Okay, like that. All right, so you know, they came in slowly like that, but then there was an explosion that blew them apart very quickly. Okay, and this is a super elastic collision. Okay, so when you have more energy after than before, that is a super elastic collision. All right, now it's funny to say that an explosion is a collision. I know that's not the way we usually think of collisions, but you know, if you think of a collision as that event where through which momentum is conserved, you know, then yeah, an explosion is a kind of a collision, because what's happening is you have a total amount of momentum before, a total amount of momentum after, and the two must be equal because momentum is conserved. Okay, the energy is not conserved if you don't know about heat, if you don't take the heat into account. And so if you're not taking the heat into account, you can get into three situations. You can get into the situation where the energy before is bigger than the energy after, and this is the most likely situation. This is known as inelastic. Okay, so it's like I had a bunch of energy before, I have very little energy after, that energy became heat. Those are the inelastic collisions. Okay, and that's the example of my rubber ball bouncing. Okay, and it bounces less and less and less each time. All right, on each subsequent collision. An elastic collision happens when E before is equal to E after, like that. Okay, in other words, there's no loss of energy. Both the both the momentum and the energy is identical before and after. Okay, and this is known as an elastic collision. They are rare at the macroscopic level. Macroscopic meaning at large size, like sizes that you can see without any kind of assistance by special instruments. Okay, at the macroscopic level, there's always some inelasticity because when things collide, there's always things rubbing up against one another, and even internally within the object. And whenever there's this internal rubbing of one part of the object against another part of the object, there's friction, and that's as soon as there's friction, there's energy being dissipated as heat. Okay, but at the microscopic level, we're talking really small microscopic, like atoms colliding with atoms or electrons colliding with electrons. There's no internal structure to say an electron. Okay, so when an electron collides with another electron, it has to be an elastic collision. It cannot be inelastic. Okay, and so that's your elastic collision. And then the third kind of collision is the one we saw right now. It's where the energy before is kind of not that much, or it's less than the energy after. Okay, and this is super elastic, and in some sense it's the opposite of the inelastic, because in the inelastic, energy goes from the macroscopic into the microscopics as heat. For the superelastic stuff, in the energy at the microscopic level, like inside the chemical bonds, is released, okay, in some kind of chemical reaction, and that becomes an explosion, which is manifested in macroscopic energy. Okay, so there you go. Those are the three different types of collisions. All right, now the next question is harder than I would give you. The way I stated it is harder than I would give you on a test. Okay, I do have two questions like this in the assignment. All right, and they're actually elastic collisions. Now, the reason they're difficult, especially the way I stated it here, the reason it's difficult is because you're going to have to solve two equations and two unknowns. All right, and the two unknowns are going to be the two velocities after. All right, now that's two equations, two unknowns isn't too bad, but one of the equations is quadratic and the other one is linear, and that's what makes these very difficult. All right. Nonetheless, I'll give you a hint at the end of this problem how to do the problems in the assignment like this, because I think some people had difficulty with that. But I do give you a hint there. I say work backwards from the answer, because it's multiple choice, so I give you 5 possible answers. Take a look at the answers. You can eliminate some of them right away. And then by just taking the answers and substituting them into the two equations, you should be able to determine which is the right answer and which one isn't. Okay, I'm going to solve it the hard way first, and then I'm going to show you how you can solve it in your in the assignment the easy way. If you know the answer, because you're testing an answer, like you say, I'm going to test answer A. Is that the right one? Well, you take the two numbers, plug into the equation. Do they work? Do they not work? Okay. If they work, well, then answer A is your right answer. Okay. If they don't work, well, then go on to B. Okay. Anyhow, let's read the problem and see how to solve it. Okay. So it's the same initial setup. A 3 kilogram mass is moving to the right at 3 meters per second, and it collides with a 7 kilogram mass moving to the left at 2 meters per second. Okay, and this time I say assume the collision is elastic, and it says what is the velocity of the two masses after. All right, now if you just use momentum to try to solve, you're going to see that you don't have enough information. Okay, so the total momentum before is going to be negative 5 kilogram meters per second. I didn't put the units in there. Let me put them in there. Kilogram meters per second, like that. Okay, and the total energy before is going to be 25 joules. Okay, why? Well, nothing has changed from above, so the total momentum before is still the same. Total energy before is still the same. All right, what about the momentum before? Okay, how would you the momentum after, how would you calculate it? Well, we have a collision, So again, those little primes there just mean, you know, after the collision, all right? So after the collision, you've got M1 traveling with velocity V1 primed, and you have M2 traveling with velocity V2 primed, okay? And you substitute in what you know that the momentum after has to be the same as the momentum before, because momentum is conserved, so that number there is going to be -5, so the momentum after is -5, okay? Let me try to align that for you. So, well, it doesn't align, that's okay. And then the, what did I do here? I know what, I just subtracted 7 V2 prime from both sides, so I get -5 minus the 7 V2 prime, that came from right there, and that isolates the 3 V1 prime like that. And then I divide through by 3, so I take -5 divided by 3, and that gives me -1.66666 like that. It's actually repeating 6, okay? And then I have minus 7 divided by 3, so that gives me -2.333333 times 2 like that, okay? And there's our equation number 1. Now if you take a look at equation number 1, that's purely coming out of conservation momentum. There's two unknowns. There's V1 primed and V2 primed, okay? So if I didn't say that this was an elastic collision, you wouldn't be able to solve it, okay? Because unless you make use of conservation of energy next, you're not going to be able to find a second equation in terms of V1 primed and V2 primed such that you can substitute one into the other and then solve, okay? So yeah, one equation, two unknowns, not enough. It's underdetermined, okay? So the two unknowns being the velocity of M1 and M2 after the collision, unknown. So we'll call that equation number 1, okay? Now, it's elastic. It's an elastic collision, all right? And that means that the energy after and the energy before are equal to one another, okay? So we could start off with an expression for the energy after. And once again, there are two masses, and so there's going to be a 1/2 mv squared for the one mass, plus the 1/2 mv squared for the second mass, and that's the total energy there, okay? That one and that one, all right? And now we can start to substitute in numbers. Let me see if I can align the equal signs here. Gets rid of that, okay? Try to align the equal signs. I don't know, it just makes it a little easier to read. Okay, let's take a look here, okay? So the energy after, that's the same as the energy before. That was 27.5 joules, okay? And then this term here, 1/2 times M1. M1 was 3, so I kind of I went a little bit faster. I don't want to go too fast for you. So 27.5 is equal to 0.5. M1 was 3, and V1 primed. We just don't know what V1 primed is, so we're just going to leave that one alone. Okay. Copy, paste like that. Okay, so we're just going to leave the V1 prime squared. We're going to leave that alone because we don't know what that's equal to. Plus 1/2 is 0.5, M2 is 7, and once again we don't know what V2 prime squared is, like that, and so we'll just leave that alone. Okay, so if you take a look at that equation, which is just the energy after, okay, you take a look at that equation and you see that there's two unknowns in it as well, and they are V1 primed and V2 primed, so that's promising because that's the unknowns in equation 1. But the problem is that they're squared, and that's going to make our life a little bit hard in a minute, okay? So in the next one, I just did 0.5 times 3, okay, and then 0.5 times 7, like that, okay, and then I get that expression there. And then what I did was I took V1 primed here like that, okay, and I replaced it with equation 1. So actually, let me say that. So now use equation 1 to substitute for V1 primed. Okay, so see that V1 primed there? All right, what I'm going to do is I'm going to take this whole expression here. I'm going to substitute in that for that V1 primed right there. Okay, now I'm not being tricky or anything, but you see that V1 primed is squared, so the negative sign doesn't matter. Okay, so that's what happened there. Okay, so you can see, you say, what did I here, I can put them back in for just a minute here. So I had a negative sign there and a negative sign there, and you say, well, why did you replace them with positive signs? Well, because the whole thing is squared, and you just saw a minute ago it doesn't matter whether you use the positive of the velocity or the negative of the velocity, okay? So if I multiply throughout here, throughout that bracket there with -1, then that becomes positive. Whoops. That becomes positive, and this becomes positive. Okay, and there we go. So we have this expression here like that. And we're going to square it, okay? And so you're going to have to use FOIL, okay? So I did a couple of steps at the same time, but I don't think it's that bad here, okay? So basically, you know, when you do FOIL, you take that and, well, it's not even FOIL. It's just basically you take the first term and you square it, okay? But I also did the first term, squared it, and multiplied it by 1.5, okay? So that's not too many steps, I hope. So take 1.66666, square it, multiply by 1.5, and I got 4.1666666, and the 6 is repeating, okay? And then for the middle term, you take the first term, that 1.666, multiply by 2.333333, okay? And you get, and then multiply that by 2, and you get 11.66666. And that's the linear term. That's the term with V2 primed, okay? So basically take that 1.666, multiply it by the 2.33333 times V2, then multiply that by 2, and then multiply that by 0.5, and that gives me that number there, okay? So that's the linear term. And then finally, the last term within this piece here that you're expanding, okay, is going to be 2.33333 squared, okay, multiplied by 1.5, and that gave me 8.166666. And that's the V2 prime squared term, okay? So here's the constant. This is the linear term. That's the one that has the V2 primed in it, and this is V2 prime squared, okay? Now that was the energy for mass 1. The energy for mass 2 was just 3.5 times V2 squared, okay? And so that's what that term is there, like that, okay? Now we can collect those two terms together, and we get this equation, all right? And you take a look at that equation and you realize it's a quadratic, okay? Now, you know, like I know that V2 primed is a bit of a noisy symbol. It's got a lot of like little pieces to it, but you know, just treat that like X. In fact, I can write that on my next line here, okay? You could just take this and, you know, I don't know if this helps or not, but yeah, maybe you'll see it a little bit better. You know, instead of that V2 prime, just call that X, and then that's X squared there like that, okay? So this is your constant term. There's your linear term, and there's your quadratic term like that, okay? Now what I did was I just divided through by 11.6666666, and it reduces to this, okay? And again, if you want to see that in terms of X, it's going to be 0 is equal to -2 plus X squared, okay? Or if you like it turned around, I mean, usually you write it like the square term first. So this is going to be X squared plus X minus 2 is equal to 0, like that, okay? And I picked these numbers on purpose because that factorizes very easily. And so when you solve for this, you get that V2 primed is either 1 or -2, okay? And you get two answers, and you say, well, why am I getting two answers, okay? And let's take a look at what that -2 means. So if you go back to the original problem here, M2 was the 7 kilogram. So V2 was negative because it's going to the left. It's -2. So down here, just to remind you, recall that V2 is equal to, so that's the velocity before the collision, the velocity of the 7 kilogram mass, the velocity of M2 before the collision. That's going to equal, to the left, 2 meters per second, like that. And you go, look at that. You got the same solution back again. Okay, you got like the same velocity as if it didn't collide. And that's right. And the reason is that momentum doesn't know about time. It doesn't really know about a before and after. So it's going to give you both solutions back. It says, well, I don't know, here's the before and after, okay? Here's all the solutions I have. You decide which is before and after, okay? Well, we know that the -2 is the before, and so guess what the after is? It's 1, okay? So we drop the -2 meters per second, since that's the original velocity before the collision. Okay, and again, all conservation laws know nothing about time. They really don't know about befores and afters. Okay, so there it is. That's v2 primed. That's the velocity of m2 after the collision is negative 2 meters per second. Okay, and then of course you say, well, but I also need v1 primed, and you say, well, what do I do? Just take that v2 primed is equal to 1. You go back to equation number 1 right here. Okay, and in there you just put a 1 for v2 primed, and when you do that you just get very simply negative 4 meters per second. Okay, so the conclusion is that that the 3 kilogram mass, so let's say here after the collision, the 3 kilogram mass moves to the left at 4 meters per second. Oh, I did say after the collision. Okay, I'll take that out. So after the collision, the 3 kilogram mass moves to the left at 4 meters per second. The 7 kilogram mass moves to the right at 1 meter per second. Okay, and so the diagram looks a little bit like this one right here. Okay, like A2. We can even call that A3, except that now I'll do it in blue here. You know, your V2 primed isn't this. Your V2 primed is 1 or positive 1 meter per second. Okay, and your V1 primed is not that. Your V1 primed is what was it again? It was 4. Okay, it was 4. So it's negative 4 meters per second. In other words, negative being to the left. Okay, and so there you go. You have an elastic collision. Now at this point you go, geez, that's a lot of work. Okay, it is. You can always solve problems like this. Okay, where you have two masses that are colliding. I tell you their masses before, I tell you their velocities before, and I tell you that it's an elastic collision, and I don't tell you anything else after. Okay, so I don't say which one's moving, how fast each one is moving. You can solve those. Okay, but the problem is that what you've got is you've actually got two equations, or what you get are two equations and two unknowns, and the two equations are, one of them is a quadratic, and so there's no avoiding the quadratic. Okay, and so you say, well, how would I do that on a test? Okay, well, on a test what I would do is something like this. I would say to you, like I would have a bunch of solutions, and so like, I'll just give you one, like A is going to be like V1 primed is equal to negative 4 meters per second, and V2 primed is equal to positive 1 meters per second. Okay, like that. Okay, and then I've got some, like I've got B, C, D, and E. Okay, now let's assume that those ones are wrong. So this is the right answer. So you go through them one at a time, and you've got two equations here. Okay, you've got you don't even need the two equations. You could just look at this one for the before. Okay, it's for the before momentum. Okay, and you've got this one for the before, or do I need the, sorry, the after, I meant the after, yeah, the after energy, and you've got this one for the after energy, like that. Okay, and now if you plug in the numbers here, okay, now they could be wrong, but that's the point, you're checking. So you go, all right, M1 is 3, V1 primed is negative 4, like that, plus, and then M2 is 7, and V2 primed is 1, like that, and you go, well, what's that equal to? Well, that's negative 12 plus 7 is equal to negative 5. And then you ask yourself the question, is that equal to P before? Well, if you look above, you'll see that P before was negative 5, so it checks out. Okay, so the momentum checks out. All right, and then you go, well, what about the energy? Well, the energy, you go, well, let's do the same thing. So for a half, we'll put 0.5. M1 is 3, and then you have negative 4 squared, but that's the same as just 4 squared, like that, and plus 0.5, and then M2 is going to be 7, and V2 primed is, what was it again, 1, like that. Okay, squared. All right, and if you work that out, I haven't worked it out, but I bet you it's equal to 27.5, like that. And then you say, is that equal to the energy before? And it checks out, and you go, good. A is the correct answer. Okay, now what would you see for maybe like B? Okay, well, if I had B here like this, I might be tricky, like I might take this and I might make the energy work but not the momentum work or something like that. Let me just change that to 3. Okay, so this one is right. All right, that's the right answer, and this one over here is wrong. Okay, all right, because that's wrong there like that. So then what would happen is when you go to check out if the momentum before and after are equal to one another, you know that the momentum before is equal to -5. Okay, we did it above. The before picture never changed, so no, so there it is. Okay, and then you go to do the momentum after, and you say, well, instead of putting a 4 there, you're going to put a 3 because that's what it, or -3 because that's what it is in part B. And then you say, okay, well, 3 times -3, that's -9, and -9 plus 7 is -2. Is that equal to the momentum before? No. Okay, no. P before is equal to -5. P after was equal to -2. Where did the momentum go? Okay, like where did that momentum go? Momentum has to be conserved. And does the answer in part B conserve the momentum? No, it doesn't. Okay, now I could have done other things. I could make the momentum work out but not the energy. All right, so you just go through them one at a time and you just check which one you think works. Start with the one that seems most intuitive. Usually I give you a few that are like kind of crazy and you go, well, that can't possibly work. So you try out you try out the more reasonable ones, and if the momentum checks out, that is the momentum before and after works, and the energy before and after works, you found your answer. Okay, so working backwards from the answer is a lot easier than trying to find the answer if you're just working without any kind of a guess as to what that answer might be. Okay, so there we go. And you know what, I've got about 20 minutes. I wanted to make this an hour long. Let's do one more. Okay, let's do one more. And this one is going to be a one-dimensional explosion. Okay, and so let's do the opposite of what we have, like I don't know, like what we have here. Okay, so this is question number 2. So we'll do the exact opposite of that. What do I mean by that? So initially, I'm just time reversing our problem. Okay, so initially, a 10 kilogram mass is at rest. Okay, it blows up. All right, I guess this is question number 4. It blows up. All right, a 3 kilogram chunk. Let me make sure I write this right. A 3 kilogram mass is found traveling to the right at I don't know what 5 meters per second. Okay, how fast and in what direction is the remaining piece traveling? Okay, let's get rid of this. All right, so let me read that again for you. So initially you have a 10 kilogram mass and it's at rest. It's just sitting there. Okay, it explodes into 2 pieces. All right, and a 3 kilogram mass is found traveling to the right at 5 meters per second. How fast and in what direction is the remaining piece? Okay, I didn't even tell you that it was 7 kilograms, but you should know that because mass is conserved. All right, so you start off and you say, well, what's the momentum before? All right, now the momentum before, this is just one mass. Okay, so we're just going to say mv. Okay, so this is the total mass before and the total velocity before. But before the explosion, So think of here the collision as the explosion. The explosion is the collision. All right. If you ran the movie backwards, you know, like pieces flying apart coming together are a collision. All right. So, you know, this 10 kilogram mass, it's at rest. So its velocity is 0. And so, you know, when you go to calculate this, it's going to be 10 for the mass, but it's going to be 0 for the velocity. And so that's 0 kilograms, kilogram meter seconds. Okay, so there is no momentum before the explosion. What about after the explosion? Well, after, it's basically this formula here. I'll just borrow it from up there. Okay, it's basically m1 v1 primed plus m2 v2 primed. Okay, and we can substitute in numbers. Momentum must be conserved, so that momentum after is 0, like that. Okay, so one thing I've noticed, you know, students in the past, they've sometimes gotten confused. They say, well, but things are moving. How can the momentum be 0 if things are moving? And that's because you're thinking maybe of momentum as energy, you know, and you think, well, everything is moving, so everything has energy, and energy just adds up. But no, remember, momentum has a direction associated with it. So the momentum to the left is going to cancel out against the momentum to the right, such that it's equal to 0. Just because things are moving doesn't mean that the momentum can't add up to 0. And that's what's happening here. Okay, so basically the momentum of m1 to the left, m1 is moving to the right. Okay, so the momentum of m1 to the right is exactly equal to, but in the opposite direction to, the momentum of m2 to the left, such that when the two add together, they cancel. Okay, so that's what's going on. So m1 is 3 kilograms, and v1 is how fast, or v1 prime, sorry, is how fast is m1 traveling after the collision. It's traveling 5 meters per second to the right. Okay, and so that's going to be plus 5, like that, for 5 meters per second. Plus m2 here is 7, like that. And v2 primed, we don't know, but that's what we're trying to calculate, right? Because we don't know how fast is the remaining piece moving. Okay, so so how do you do that? Well, let me just simplify this. Is equal to 0 is equal to 3 times 5, which is 15, plus 7 times v2 primed. Okay, and if I take the 15 to the other side and divide it by 7, I'll get v2 primed is equal to negative 15 divided by 7, and that's just a little bit bigger than 2. Let me get out my calculator and work that out. So 15 divided by 7 is this number right here. Okay, with a negative sign in front, and that actually rounds up to 3, like that, meters per second. Actually, we round only 3 significant figures, so there we go. Okay, so that's the answer. Okay, so the answer is that after the explosion, well, write it down. After the explosion, the 3 kilogram is moving to the right at 5 meters per second, and the 7 kilogram is moving to the left at negative, or just 2.14 meters per second. The negative part is what you mean by left. Okay, and so there you go. There's an example of an explosion. You might say how much energy was released in this explosion, and so we could do that too. So what's the energy before? Well, the energy before is 1/2 mv squared, like that. Okay, and once again, the velocity before is 0 because this mass is not moving. All right, so 0 joules to start with. The energy after is going to be, well, let me just steal it from up here so I don't have to retype it all. There we go. Okay, you've got 2 masses, right? So there's m1 moving with velocity v1 primed. Okay, right there. And so 1/2 mv squared for mass number 1, and here's 1/2 mv squared for mass number 2. All right, like that. And now we can substitute in the numbers. That's going to equal 0.53, and v1 primed was 5, so that's 5 squared, like that. okay, plus 0.5 times 7 times 2.14, like that, squared. Okay, again, negative 2.14, positive 1.14 doesn't matter because when you square it, it works out. And let me just do that on my calculator very quickly. It's equal to we'll round that off, okay, 53.5 joules, okay? So wait a minute, 0 joules to start with, and then 53.5 joules after. You go, where did that 53.5 joules come from? And it came from whatever, like you might imagine a little bit of TNT in there, some explosive chemical, okay? And, it's just sitting there, and then it suddenly explodes. The energy, that 53.5 joules, that was in the chemical bonds of the explosive material, okay? And then once that explodes, it transfers that energy into the motion of the two masses that are flying apart, okay? And there you go. There's an example of an explosion, okay? Now, these are all 1D problems, and I purposely did 1D because, I had a whole series of 1D problems in the assignment, and some people did ask about them, okay? So there they are. Now, they are a little bit easier than the 2D because the 2D has the addition of vectors, okay? But in my other tutorial video, I have that, okay? I have like a 2D collision, and I did quite a bit on 2D collision even in my lecture video. So I didn't want to repeat with yet another 2D problem. If you're having difficulties with 2D collisions, take a look at those ones, okay? But now you have the 1D, okay? And the other thing you should look at are the center of mass problems. There's 1D versions, which are really easy, okay? And then there's the 2D version. But once again, I have a 2D version center of mass problem in my other tutorial video. So please take a look at that one, okay? All right, I think that's enough for our impromptu live stream. All right, let me see if there's any questions in the chat. And nope, no one joined the stream. That's okay. Hopefully you'll watch this later and it's helpful for you. Bye-bye.